So as I say, that first bit of growth and decay was a very simplified model that two look at. They pretty much stick with that model. In extension one, we, well, strangely enough, extended. Weird that, hey? So now we're going to take into account some external conditions. The classic one is to do with temperature. So the idea that the temperature of an object can never go lower than the temperature of its surroundings, unless of course you apply things to it. But if you apply ice to it, then the temperature of your surroundings has changed because now it's the temperature of the ice itself. So we change the equation to take this into account. So to P to T, instead of this being Kp now, it's Kp minus some constant, but we tend to factorise it and go Kp minus n. Kp minus n. The solution to this, and again we're allowed to just quote the solution, but you could derive it the same way as I derived the other one, playing around with the turn upside down and logs come out. There's your trivial case in this case. Again, we don't really worry about the trivial case. So instead of p equals 0 for the first case, it would be p equals n would be the trivial case. The situation we're more interested in is this one. P equals n plus ae to the kt. Now if you think about that graph, we've got our exponential curve, but it's been shifted up to n. So instead of going asymptotic to the x-axis or the t-axis, it's now asymptotic to p equals n. So that external condition, if we were talking about temperature, it's going to go asymptotic to that temperature because it can't drop below the temperature. So we end up with a horizontal asymptote on the graph. P is still population. N plus A would now be the initial population. If you think about it, because sub in t equals 0, you'll get N plus A. K is still our decay or growth constant. T is still time. Quite an old question, but it does illustrate the classic cooling idea. So 1993, T is the temperature inside the room, A is the outside air temperature. Now Newton's law of cooling states that the rate of change of temperature is proportional to T minus A, so they're basically setting it up for you. Show that, as I say, they tend to say show this as a solution. So rather than getting you to spend time deriving the solution, they give you the solution and say, well look, show that this works. So T is equal to A plus CE to the KT satisfies the law of cooling. So if T is A plus CE to the KT, remember I'm trying to show it's equal to some constant times T minus A. Differentiate that, dt dt, so it equals KCE to the KT. But hang on, we know T minus A is CE to the KT, so I just got to rearrange what they're asking me to show. So yeah, okay, we get some constant times T minus A. So yes, it does satisfy. So yep, we know that T equals A plus CE to the KT is in fact a solution to our differential equation. They now tell us that the outside air temperature is 5 degrees Celsius. Certainly not currently, we must be talking about winter. And a heating system breakdown causes the inside room temperature to drop from 20 to 17 in half an hour. After how many hours will the inside room temperature be 10 degrees? All right, let's put it all together. So 5 plus CE to the KT, because that outside air temperature is going to be the asymptote, if you like. So we know it's going to be 5 plus CE to the KT. The initial condition was, where is it? So initially it's 20. So C must be 15. Remember we said those two things must add together to give the initial one, but again, formally you can show that C is 15. So we now have a formula, 5 plus 15 e to the KT. We now need to use the other piece of information to work out the constant. They've told us it drops from 20 to 17 in half an hour. So when T is 0.5, I now know the temperature is 17. I can rearrange that eventually. Let's find K. It's, again, an exponential equation to solve. 2 log 12 on 15. Again, I haven't really worried about simplifying it down, but I can store that value in my calculator, or I can play with exact values. It doesn't really matter. So all right, we now want to know when T is 10. So we want to know when 10 is equal to 5 plus 15e. Again, I've just written it as K. Haven't put the value down. So 15e to the kt will be 5. Eventually I get t is 1 on k log of a third. So I go to my calculator, and I've got that constant stored in there. I get 2.46167. So the question was, after how many hours? Well, I couldn't help myself. I said after 2.5. I mean, technically, if we're talking about whole hours, I guess the answer is 3 hours. But I mean, so close. I think as long as you've got your final answer down, I mean, you can justify your final line there. So after 2.5 hours, it's dropped to 10 degrees. All right, so there's a classic example of the Newton's cooling one. So again, handful of questions, 7 H's on our extended growth and decay.